Okay, let's talk about rotational work. Real quick review, linear work. Linear work is force times displacement, and therefore again, the force and the D have to be in the same direction. If force is this way and D is this way, no work. That's just a quick review. Okay, let's go on. Let's go on and talk about rotational work. Now, first of all, in order to understand rotational work, we need to understand what a radian is. A radian is nothing more than, if this is my circle, around every circle there are 6.28 radians. If you really want to think of it, it's really just a radius. But if you draw the radius out here, you get that subset of a circle. Around the circle, you're going to have, well, 1, 3, 4, 5, 6, and a little piece. That little piece is the 0.28. There's 6.28 radiuses around any circle. Now, radian's the term we use, but this is really nothing more than a radius out along the surface of the circle. So it's important to understand that. The key thing to understand is 2 pi radians is equal to 1 circle. But in our terms, we'll use the term revolution a lot. So 1 complete revolution. So one thing you'll be expected to do is be able to go from radians to revolutions. So if I say 3 revolutions, and I want to convert that to radians, I do it this way. I put revolutions on the bottom, I put radians on the top, and I know that 2 pi radians is equal to 1 revolution. So therefore I would have 6 pi, which is of course 6 times 3.14, which is going to be about 18 point something. So let's just put approximately 18.8 radians. Anytime you see pi, that means radians are involved. Another thing you'll be asked to do is to go from revolutions per minute. Let's say we have something, let's say 3,600 revolutions per minute, and I want to convert that to radians per second. There's 2 separate things you have to do here. First of all, we need to get rid of the revolutions. So I'm going to do it this way, 3,600. It's important when you're doing fractions to write them this way, because now I'm going to multiply this by another fraction. Now, I want to get rid of revolutions, so I need to put revolutions on the bottom. I'm going to cancel out units the same way we would cancel out numbers. So I want radians on the top. And of course, I know that 2 pi, 6.28 radians, is equal to 1 revolution. That allows my revolutions to cancel out. That's going to leave me with radians per minute. So now I need to get rid of minutes. Minutes on the bottom. I need minutes on the top to get rid of them. And I need seconds. Now make that fraction equal to 1. And of course we know that 1 minute is equal to 60 seconds. So then you need to do the math. 3,600 divided by 60 becomes 60. 60 times 6.28, 3,600 approximately, I don't have a calculator, so you can do it with a calculator, about 370 radians per second. Okay. Now let's take a look at our work formula for circular work, and its work is equal to torque times theta. So torque times theta. Now, if you remember, theta really, it's kind of weird. Theta really doesn't really add much in the way of a unit. Our work units are still going to be based on the work units we saw before in the English system. It's going to be pounds times feet. I don't care if you also write foot-pounds. In the metric system, it's going to be newtons times meters. So those are both units of work. Now, Let's take a look at this. Now, when we're talking about something moving in a circle like this, well, it's important to understand the force is going to be tangent to the circle. It's going to be along the edge of the circle. This is going to be pulleys and gears and things like that. The lever arm is that distance there, and the lever arm is actually the radius of the circle. So in other words, if I have something like, think about a bicycle. If you have a bigger lever arm, you sit there and you change the torque by doing that. That's why you have a big lever arm on the sprocket that's where your pedals are, a small lever arm on the back sprocket of the bike, excuse me. So work is equal to torque times theta. Theta is nothing more than the angle that you go through, but it's got to be in radians. Again, 2 pi is equal to 1 revolution, and of course from our basketball fans all know that's 360 degrees. So let's do a sample and make sure we can apply this. I'm going to apply, let's go with a bicycle. 100 Newton force on a pedal of 6 centimeter radius. So in other words, that's your front sprocket on your car, on your bicycle. That's 6 centimeters. Here's your pedal that your foot is pushing on. That's your foot. That's attached to your body and all that stuff. Man, I should have been an artist. And what I want to know then, in 3 revolutions, how much work is done? And again, we'll always give you the equations. So work is equal to torque times theta. So now, torque is force times lever arm. So it's force times lever arm times theta. Now if we plug that in, my force is obviously 100 newtons. Now here's where you have to get careful. 6 centimeters. 6 centimeters is equal to 0.06 meters. Now that's a change you should be able to make. 0.06 meters times 3 revolutions. But remember, 3 revolutions, 1 revolution, 2 pi radians. Sorry, that one kind of ran off the edge of the page. So you're going to multiply all those together and get a value. Let's go ahead and do it. Handy dandy calculator. I'll take in case you've never seen anybody run a calculator. 100 times 0.06 times 3 times 6.28 equals 113, we'll just round it off, 113 Newton meters of work. That's how much you do making 3 revolutions with your bicycle pedal. You're doing work. You're going to cause your bike to go down the road. Hope this helped.